Welcome to this video on using Hess's law to calculate enthalpy changes indirectly. And in this first of the videos we're going to be focusing on using enthalpies of formation in order to do this. So first let's have a brief recap of the enthalpy change of formation, and we're going to use the formation of carbon dioxide as our example. So this tells us that it's the heat energy change when 1 mole of a substance is formed. So we need 1 mole in front of the CO2, and that's in fact what we've got in this equation. It's formed from its elements under standard conditions. So we've got elements, carbon and oxygen, and it says here all reactants and products in their standard states. So if we think about the reactants, if we're going to use carbon, its standard state would be graphite, and that's assumed here. We could write that, but it's a solid. When we consider oxygen, its standard state is actually in terms of diatomic molecules, and they are in the gas phase. Carbon dioxide itself is also a gas. So this would be the equation corresponding to the enthalpy change of formation of carbon dioxide. Now, pause the video and see if you can write the equation where the enthalpy of reaction would correspond to the enthalpy of formation of calcium carbonate. Well, I wonder how you did. Let's begin. So we're going to have a reaction arrow. We're going to form 1 mole of calcium carbonate, and the standard state of that is a solid, and that means we need carbon, standard state solid, we need calcium, standard state solid, and we need O2, standard state gas, and because we've got 3 oxygen atoms here, we need 1.5 or 3 halves O2. Well, that's enthalpy of formation. Let's get on to see how we can use these to calculate enthalpy changes indirectly. Our first example is a reaction indeed involving calcium carbonate. And what we've got here is various enthalpy of formation values. So whenever we're doing these sorts of problems, we need to follow the same basic procedure. So the first thing we do is to try to form a Hess cycle here. So we need at least one point here that will connect both the reactants and the products. And enthalpies of formation which go from the elements, I'm going to write elements down here, to form these compounds are going to help us. So if we consider calcium carbonate, we found last time that what we needed, well, a few moments ago, was that we need calcium, we need carbon, and we need 3 halves O2. And if we take those values there, those substances there, and we turn them into calcium carbonate, we find down here that the enthalpy of formation in order to do that is minus 1207 kilojoules per mole. Now we'll add on here our enthalpy change that we want to find. Now then we're going to need to complete the cycle by looking at how we would form calcium oxide. Well, we can see there that we need calcium and we need one half of O2 in order to do that, and that's going to release 635.1 kilojoules per mole. And the formation of CO2, we've got carbon that was left over, we've got 1 of the 1.5 O2s left, and so that is sufficient to form carbon dioxide, which is going to release minus 393.5 kilojoules per mole. So this is our Hess cycle complete. So once we've completed the cycle, we then need a statement of Hess's law. And remember, we can either go for the 2 roots, so we can look here are our elements, that's where all the arrows start, so this is our start point, and we can see that we can either go along the red route to get to the finish point where all these arrows end, or we can go along the blue route, which is here, starting where these arrows all start and finishing where all the arrows end. And just like last time, we see that if we had a clock in the middle here, then the blue arrows have got the anti-clockwise sense and the red arrows have got the clockwise sense. So we're going to state here delta H root 1 is equal to delta H of root 2. So now we just fill in the enthalpy changes, and I strongly encourage you to fill in the values in brackets here just to let the calculator deal with the complexity of subtracting involving minus signs. So the blue root I'm doing first is that. The red root is minus 1207 plus the enthalpy change that we're interested in finding out. And Hess's law tells us that the enthalpy change along those two routes must be the same. So now our third stage, once we've equated our two expressions that corresponded to the total enthalpy change along the two routes, we then solve for our unknown. We take delta H there. We subtract this value from both sides. If we add these up, we're going to find that they come out to be minus 1028.6. We're going to subtract from that minus 1207.0, and we can find out from that that our overall enthalpy change that we're interested in finding has a value of plus 178.4, and that will be in units of kilojoules per mole. So the four stages that we need to be aware of. Stage 1, the cycle, construction. Stage 2, adding on enthalpy changes. Stage 3, equating the enthalpy along two routes. And stage 4, solving for the unknown. So those are our four steps in finding an enthalpy change indirectly using Hess's law. One final example, and it would be good to see if you could pause the video now and have a go at applying that technique to solving this example. Well, let's see how you got on. So again, we're going to have the elements down here. And in this case, we've got on the either side you can do, we've got 2 carbons, we've got 6 hydrogens, so we need 3 H2, and we've got 7 oxygen atoms, so that's 7 halves O2. Just put a box around them. So now we have to go from the elements up to the products, and for ethanol here we find that value there was minus 277.1. Now when we look at the table here for oxygen, we actually find that our value is 0, and that's an interesting point to note here, that this value is 0, and that's because the enthalpy of formation for elements in their standard states is 0, and that's always going to be the case. To turn oxygen gas into O2 gas doesn't need or release any energy. Now let's continue. So when we come over this side, we want to connect the elements up to the 2CO2, and we immediately encounter another complication, which is that the enthalpy of formation of carbon dioxide is minus 393.5. But in this case, we're actually not making 1 mole of carbon dioxide, as the enthalpy of formation's definition suggests, but we're actually making 2 moles. So the enthalpy change to go from 2 carbons and 2 O2s to make 2 CO2 is actually 2 times minus 393.5. So we must make sure that we're including these numbers, otherwise our overall enthalpy change will be incorrect. Now here we need to make 3 H2Os, so this time we need to treble the enthalpy of formation of H2O, because that would have been just for making 1 mole of H2O. So we need 3 times minus 285.8. So now that we've got our enthalpy values put on, we need to consider our two roots, or our clockwise and anti-clockwise arrows, and we can see that these arrows here are always going in a clockwise sense. They're always going around the clock that way, whereas these arrows that I'm going to do in blue are the anti-clockwise arrows. And you can likewise see that if this is our starting point where all our arrows are birthed, then and this is our finishing point where all our arrows end, we can either go along the blue route or we can go along the red route in order to get there. So we have our expression of Hess's law now, which is that if we take all the enthalpy changes along the red route, we better put on our enthalpy change that we're actually trying to find. So minus 277.1 plus delta H must now be equal to the enthalpy changes along the blue route, which would be 2 times minus 393.5 plus 3 times minus 285.8. And if we then rearrange this to solve for delta H, we can then find that on the right hand side we have minus 1644.4. We are subtracting from that minus 277.1, and overall that gives us a value of minus 1367.3. Sorry, that's not a very good 3 kilojoules per mole. And that was how to use Hess's law involving enthalpies of formation to calculate enthalpy changes indirectly.